Okay, so welcome everyone. I want to present 5G networks, and I want to start with basic evolution of technologies in terms of networking, and then also how the 5G network has been changed compared to 4G. So if we start with the software-defined network, that's the basic technology that we need or it's integrated as part of the 5G. So to understand the software-defined network, first we need to look at the past, how the physical networks or how the fixed network have been evolving. So primarily the network has been quite static, or they have been quite fixed in the sense that all the networking was managed with specialized applications, specialized operating system, and then hardware that was very integrated into that software. So everything was quite integrated from the vertical point of view, from the hardware up to the software that was managing those networks. And then incrementally, this sort of vertical monolithic infrastructure for the networking has been breaking down. So all the hardware has been optimized and then has become a commodity. And then the software on top of the hardware has been evolving. They have been creating a set of interfaces between the hardware and the software, so to manage all this networking. We saw this happening with the PC, for example. So the PC originally was really integrated, and then it was becoming more like a commodity. So normal hardware then could be running a different operating system, like Windows, Linux, BSD, Mac. So in that sense, all this vertical infrastructure, or this vertical technology has been separated. So separating the hardware from the operating system, and then the applications on top of that. Then similarly, something happened with the mobile networks. So basically, this same story was the basics for the mobile networks at the beginning. So everything had to be optimized, everything had to be integrated as a very monolithic solution. So in that sense, over the time, the mobile network has been suffering or has been evolving in the same way as the fixed networks. So that was happening, for example, lately with the operating system that have been separated from the hardware. So now we have Android as operating system, or we have the Mac operating system that then is running on a commodity mobile devices and so on. So this kind of trend has been the motivation in the networking. So basically, at the beginning, all the network has been deployed in fixed infrastructure with a huge set of hardware that then has been over time separated. So basically, this specialized hardware has become a commodity, and then there's a control plane that is interacting with that hardware. With that control plane, then we can define different features that this hardware can do for us. So in this case of the switching, all the components that are managing the packets at the low level, that has been sort of focused into optimizing the behavior of the packet management. And then on top of that hardware, then it's been defined an interface, which then that interface allows to implement a different control plane. So this kind of interface then helps, so for example, not only in fixed network, but then as we will see in the mobile networks, to implement different functionality, depending how we want to treat that packet. So before, all this was part of the hardware. So the hardware was including all the physical components, the operating system, and the applications, what that decide what to do with the packets when they arrive to the network. Now, with this separation of the hardware, the control plane, then we can design applications in the same way that we saw, or we have seen the applications that have been designed for the mobile devices. Same thing then can be done now with the network. So basically, we can implement applications that perform certain logic and then use those open interfaces to interact with the operating system and then with the hardware to tell the hardware what exactly needs to be happening with these packets. Oops. I'm running back. Yeah, so as an example of this functionality or applications are the routing protocols. So basically, the routing protocols like BGP, OSPF, or even some other applications like creating VPNs or whatever, those can be done as a separate applications on top of this operating system. And this helps in improving these applications. So basically, in the past, all this had to be together in the machines. Now, with the possibility of separating, then it helps to isolate the problems and then helps to improve some of this, the implementation of those applications. So then the idea is that all these components then allow the network to be more flexible. So for example, if now we invent a new application, a new routing protocol or whatever, then that can be deployed without having to change neither the hardware nor the operating system. So those open interfaces allow the deployment of new applications that can be installed and run on existing hardware and system. So this kind of background for moving from vertical infrastructure or vertical system into more like a layered or sort of more like a distributed system where the applications can be evolving separately from the hardware. That's one of the features that we will see is taken into use in 5G. And then it's taken into use mainly for managing the mobile network, managing the mobile backhaul network. The mobile backhaul is the one that connects the base stations with the rest of the modules that take care of the 5G connectivity. So in that sense, the network, this software-defined network, as we see, is the result of separating the infrastructure from the applications. And that software-defined network allows to implement this kind of applications with specific functionality. So for example, we see that we could implement a firewall with a few, well not few, but at least a separate logic and implementing an application independently of the operating system. With this open interface, we are looking to OpenFlow. OpenFlow is an open standard that defines this interface between the hardware and the applications. So with OpenFlow, the idea is that we can define different logic that is based on a match and action. So basically, match means that when there's a packet coming into this network component, if that packet is matching a logic that we have defined, then the router will take an action based on that. So those actions means that, okay, this packet needs to be sent to a different location, depending on what is the type of match that is happening with the incoming packet. Or then the action could be that we want to rewrite this packet. So basically, we want to change some of the functionality of this packet. So this, to give you an example, could be the case that there's a packet coming from the mobile. That packet then is including some malware, is including some sort of attack. So we can, with this kind of functionality, we can identify that if there's a pattern that we can see in those packets, then we can set a policy in the network that tells that, okay, if we see this packet coming in, then this packet needs to be forwarded or needs to be dropped, because we have considered that this is a malicious packet or something. So in that sense, this kind of logic with the separation from the hardware and the applications make it more dynamic, this kind of policies that can be established in the whole network. So in that sense, we can define a lot of rules that and the actions that will be applied when this packet comes into the network. So in that sense, for example, another possibility is that if there's a packet that we want to assign a different priority, then we can set a rule, a match parameter, that when this packet then is received, then we can tell that the action consists in like applying different priorities. So basically we can tell that the certain packets from specific applications or users that are connected to the network, then we can specify what kind of treatment we want to have in those packets. In that sense, we can apply like a quality of service on a need basis. And this is dynamic, so it doesn't need to be hard-coded or implemented once and then integrated in the hardware. With this flexibility of separating the hardware from the applications, then we can do this on a runtime. And that's one of the features that we'll see is an added value in the mobile network. So in this sense, this kind of open flow functionality, then we can specify concrete actions that we can use in the mobile network. So then if we move into the specifics of the mobile networks, so now we have seen that the transport part of the mobile networks, we can utilize this software-based technology. So basically we can define a set of policies to treat differently the packets that are coming into the network from the mobile devices or from the end users. So now if we look at the 5G network itself, just to give you an introduction, now assuming that the transport is more or less clear at the physical level and is software based. So in the 4G network, first we look at two parts. One is the part that is handling the control, and then the other part that is separated already in the 4G is the part that takes care of the data plane. This is again one of the main differences from the previous mobile networks. So in 2G and 3G, all this was still integrated. So basically, in the mobile networks has been happening the same mechanism that has been in fixed network, in the transport network. So as we saw in the fixed network, everything was integrated in the hardware and then incrementally has been moved or separated hardware from operating system and software. In the mobile networks, 4G was the first type of network where the architecture was taking this first step. So from 2G and 3G, now in 4G they were already separating the control from the user plane. So what is the control plane in a 4G network? It's basically the first steps, the first messages that happen when the mobile is connecting to the mobile network, to the base station. So the first step is that the mobile needs to be authenticated. So the network, one of the key advantages of the mobile network from the beginning is the security and privacy. So in that sense, the mobile, when they first connect to the radio, to the base stations, then they should signal to the system what are the IDs, what are the credentials that they are given by the operator. So the operator has written that information into the database, but then that same information is written into the SIM card, which is then included in the mobile. So that means that when the mobile first connects to the network, then as part of the signaling, then the network needs to go to a database and then compare that this information is valid. And then the network starts authenticating the user. So basically, the network has to ask the users to some proof that this device is the one that it's claiming to be. So in that sense, in this part of the signaling, the mobile and the network, they start handshake. So basically, they start sending like a token, which then the mobile has to confirm, and then has to verify and send some token back to the network, which then will also verify and then compare to make sure that this device is trusted. Once this first signaling for the security is completed successfully, the next step is that we need to assign a connectivity session to that user. So basically, in order to assign a connectivity session, the network needs to assign an IP address to that mobile. And that's still part of the signaling. So in the first security mechanisms, the entities that are involved in the 4G is what is called the MME, which is the mobility management entity, which is taking or checking this security information from a database, which is the Home Subscriber Service, HSS. Then for assigning the IP channel or the IP address that will be given to the mobile, then the MME has to connect to the gateway. So basically, what we have is a gateway that is going to serve that device, which is serving gateway. And then together with that serving gateway, there's a separate gateway, which is managing all the packet data, which is packet data gateway. So once those gateways agree that this is the IP address that we can give to that device, then the MME informs the device about that IP address. So from that point on, all the data coming from that mobile will be sent with that IP address that has been given by the mobile network, by the core network. So all the data from those applications, YouTube, browsing, pinging, whatever you want to do from the mobile will be coming to the network, to the mobile network, using the IP address that has been assigned to that device. But then the thing is that this device will be moving across the network. So basically, normally when a device moves, then this connection is broken, because then the device is out of the coverage of that specific base station, and then needs to reconnect to another base station. So in order to maintain this connection, because the idea is that the mobile networks should make it seamless, this kind of mobility. So basically, in this sense, the IP address that's given to the device is maintained, but then that IP address will be then encapsulated into another IP address by the base station. And that encapsulation then allows the mobile to move around while keeping the original IP address given by the mobile network. But then when that device is in another base station, then the base station changes the address that is used to encapsulate the data. So basically, it means that from the UE, from the mobile device to the YouTube application, they have the same IP address all the time. But then on the base station, when they change, the IP address that is used for the encapsulating is changing, because the device is changing to a different base station. So this is a bit of the basics of mobile networks and how they can support this mobility while keeping this kind of IP address during the whole lifetime or the connection of the mobile. So if we look at a bit of more in detail what is happening. So if we look first at the signaling, so first what comes to the signaling, there are a set of protocols between the base station. The base station in 4G is called E not B. And then the MME is the one, the entity that is taking care of mobility, authentication, and then signaling the IP address to the device. So In that sense, this signaling is happening in a set of protocols. So it's as we see, first starting with an Ethernet, and then on top of that we have several transport protocols, which is SCTP. And then inside the SCTP, then we have the specific messages part of the signaling. So basically that's called the S1 interface, or S1 protocol. So then the MME then needs to talk to, for example, to another MME to inform that this user is moving around. Or then the MME needs to inform to the gateway that now this user needs to be allocated this IP address. So then between the MME and those S and P gateway, serving and packet gateway, they will communicate also still using the IP UDP and some specific signaling, which is called GTP, GPRS Transport Protocol. So with these protocols, the base station, the MME, and all those networks, they start exchanging all the required information to allow the UE to get this IP address. But then once this information is exchanged between those entities, then the UE needs to send the data to the network to tell the network that I'm a trusted device. This is my ID. This is my security token, and so on. So then, on top of that, the UE has to encapsulate that info in what is called NAS, which is another protocol that is used directly between the mobile device and the MME. So for example, in this NAS message, what we include, or what the mobile include, is all the SIM information that will be used to authenticate that user. So once all this signaling is completed, then all the data starts to happen. And then the data, as we saw, also it's end-to-end is IP, but then underneath the data, then it has to be the encapsulation. So basically the encapsulation that I mentioned that will be done between the base station and the gateways that are handling all the user plane. Then that encapsulation is happening on top of IP. So as we see, the data coming from the mobile comes with it as part of the IP end-to-end connection, but then below that, there will be another IP layer, which is the one that is changing between the base stations. So basically that IP layer, it's changing when the device moves from one base station to another. So if we look at the higher level at the mobile network, this is how a normal deployment of a mobile network looks like. You might have thousands of base stations. But then under those base stations, then there should be like a physical connection, which, as we indicated, can be based on this software-defined technology that allows to set different policies. So all the data that is coming from the base station then is transported using this normal Ethernet or fiber, or then some sort of managed software-based technology. And then the data is encapsulated in those tunnels. The IP that is used between the base station and the core is the one that is changing. And then inside this IP tunnel, which is the GTP tunnel, is established every time that the device changes from one base station to the next. And that's translated in a set of multiple tunnels. So for example, for different applications in the same device, there should be a different tunnel. So that means that the tunnel is encapsulating all the data that the mobile is sending for some specific application. And then the base station then is sending that to the specific packet or serving gateway. So each device will have multiple tunnels depending on how many applications are running in that tunnel. So, and then with the software-defined network, what we do is that we can apply different policies, so we can assign different priorities to those tunnels. So we can do that dynamically using this, the idea of this software-defined technology. So if now we move from the 4G into the 5G, one of the main differences is that as you see in the 4G there was the MME, the HSS, that is the database keeping all the information about the users, and then the serving and packet gateway, which is taking care of transporting the data. Now in the 5G there are more components, there are more modules. So basically, in addition to the MME, which now in the 4G is called AMF, Authentication and Mobility Function, then we have another component which is somehow replacing the serving gateway, which is the Session Management Function, SMF. And then we have the packet gateway, which is the one that now is user plane functionality, UPF. So those functions, we could say that map more or less one-to-one with the ones that were available in 4G. But now in 5G there are more functions. So basically we have like NSSF, which stands for Network Slice Selection Function. We have NRF, Network Repository Function, NEF, Network Exposure Function. So these new functions, they have a new role into this 5G architecture. The role is that these functions allow a more service-based type of architecture. What does it mean? It means that now these functions are more dynamic. So there will be a repository, which is the network repository function, and that repository then keeps track of the functions that are active in the network. So that means that if there are new functions, then they can be added into the network, and then they can be registered into the NRF and made it available to the other functions. So that means that if now I invent, or the operator invents a new function, which is say that, okay, gaming function, that gaming function then could be registered into this architecture and made it available for the other functions, saying that if there's a user coming into the network that is looking for this specific application, then the remaining applications can search into this repository function, NRF, if there is such a gaming function. And then since that function has been added and registered, then it will be visible to the other function, and then that could be taken into use. Then the other component is, or the other feature in 5G is slicing. So basically, with slicing, the idea is that the network is separated into a small sub-network. So basically what they are called slices. And that means that this network then can be allocated, for example, to different entities. So let's say that this group of friends that they want to do or reserve a part of the network for the gaming, they have already their applications in the network, but then the operator can offer them a slice of the network only for their own use. It's like a group of friends, they might become like their own, they can use their own network. And that means that all the other users will not interfere with this group of gaming users. The same applies, so for example, for machine type of communication. So the operator can slice the network and then allocate one of these slices for machine type of communications. So this is the case that adding these new functions then become more flexible, and it allows the operator to slice the network, to add new functions depending on the needs of services or the needs of the different groups of users that might require their own private network. And that's the other thing that is being added in the 5G, the idea of non-public networks. The idea that someone can request either from the operator or they can build their own private network. So in that sense, someone, if they have the appropriate license, they can build up their own private network, which could be like the group of friends, the gaming. They can build using the one slide from the operator. Or then, for example, if they are in a shopping mall or whatever, they can build their own non-public network. And then they can use for their own usage this network using the allocated frequency. So in that sense, one example of this non-public network is mainly for industrial usage. So for example, let's say that we have a manufacturing company or a chemical company, mining company, construction, even the shopping mall. The shopping mall here in our campus, they could build their own private network. They could set up some indoor base stations. They can set up their own mobile packet core, and then they can provide their own SIM cards. So that means that when the users are in a factory, in a shopping mall, or whatever, they could be accessing that specific network, and then they can offer the services that are deployed in that specific network. So in that sense, this allows a new segment. So basically, it's not anymore of the previous networks that it was mainly for consumer data, for consumer market applications and so on. But now, with this kind of 5G network, the idea is that small companies or factories or whatever can deploy their own network and then utilize this instead of Wi-Fi. So for example, with the improvement in resource management, so there will be a whole radio technology that is allocated with their own interference management, etc. Security, I mean, all the SIM-based type of security is then part of this mobile network, even if it's private. So in that sense, 5G is bringing a new model to the previous mobile networks. So in that sense, one of the features that we have, or the benefit that we have, is that here in the campus, then we have this possibility of having our own private network. So in that sense, we can explore what are the added value of having this kind of network. So basically, we have complete infrastructure with base stations that have been donated by Nokia. Then we have sort of a license that is given to us by the local government authorities. So in that sense, and then we have our own packet core, which then we can deploy and utilize freely. So in that sense, we are sort of exploring what kind of advantages we can get with the 5G in this area. And the idea is that with this possibility, then we can utilize this infrastructure for different research projects. So we have a set of projects that we can explore and analyze how, for example, drones could be used and connected to these mobile networks. So in that sense, the campus, we have several base stations covering the whole area in the campus, and then we are offering these for SMEs and so on, so to see how they can explore all this low latency and functionality. And this is a bit the layout, so basically the graphical interface that then we use to write our own SIM cards and then to connect our own devices to the network. So then the other feature that we are adding as part of the 5G network is the edge computing, multi-access edge computing, or MEC. So together with the slices that we mentioned, that allows to separate the network into small segments or sub-networks, the other feature that is coming in 5G is the edge computing, which in practice means moving the computing to a location that will result in lower latency. So in normal networks, all this processing, as explained in the architecture, happens after the packet gateway. So basically, the base station is tunneling all the data coming from the mobiles until the packet gateway. And then after the packet gateway, then all the packets from the mobiles are sent to the destination, whether it's YouTube or Google or whatever. But then those applications that require low latency, they cannot go all the way to the packet gateway, do the processing, and then coming back, because that's adding extra delay to all this round-trip communication. So one of the features of 5G is moving this processing from this centralized location into more local places where this computing can be happening, and then reducing this end-to-end delay between the base station and this processing. So that means that all this, the packet gateway that was centralized, then it can be moved beside the base station. So that means that as soon as the messages from the mobile reach the base station, from the base station then they can be processed physically in the base station or quite close to the base station. So then they don't have to travel all the way to the packet gateway, which might be quite far from the base station. So in that sense, the 5G architecture defines the mechanisms to identify those devices that require this low latency, and then allows to move the application to the place where this device is located, the device that requires this low latency. This is one example of network slicing. This is basically a real deployment that we implemented, as I mentioned, in the infrastructure that we have in the campus, where we assign a different packet gateway to the device that requires this low latency or low delay. So in that sense, as an example, we choose one gateway between Finland and Korea, and the other gateway that was located physically beside the base station. So that means that when the device connects, we set in the system that, okay, this device requires a normal internet, so then that connection went all the way to Korea to do all the processing and so on, versus another connection from that same device that then we assigned to become fast internet. So in practice, that means that this device was allocated the gateway close to the base station. The result is that we can get some processing in the order of a few milliseconds compared to the processing or the delay that we reached going all the way to Korea, where there was more than 400 milliseconds communication between the two sites. So for those applications that require this low latency in the order of milliseconds, this kind of edge computing allows to deploy this kind of setup for those specific services. Then the other feature that, as I mentioned, is the network slicing, which I said. But then one concrete example of the slicing that we use is for example, for IoT data. So basically, the thing is that the IoT might result in an explosion of a lot of data. I mean, there are thousands, millions, billions of IoT devices, and we don't want to have those devices to interfere with the data from a normal consumer or those applications that require this low latency. So with the network slicing, then we separate the traffic from those devices from the other traffic. And then here is that when we already apply, for example, this software-based networks, the SDN technology that I mentioned as a part of the evolution of the transport, that, for example, is applied here to tell the switches or the routers that, okay, when there's a packet coming with this type of traffic, remember there was match action. So we tell the switches or the routers in the transport network that when there's a packet coming with this match, then this packet needs to go to a different switch, because we don't want that packet to be mixed with the packet that is coming from the consumer data or with the packet that is used for these low latency applications. So in that sense, this software-defined network, then we can already utilize in this concrete example for network slicing, where we separate the different traffic to make sure that each traffic receives its own resources, depending on the requirements. And then another feature that, well, it was already in 4G and then is coming also in 5G is the narrowband IoT. So basically means that data or radio that is mainly for transporting data or this communication from small devices. So basically with this, then the devices with these IoT devices then will have its own signaling, will have its own transport. So then they send the small packets and then they require a specific transport. So this allows to use the same network for IoT data. And then the last feature that it's already or was already in 4G is MBMS, which is basically how we can utilize the mobile network for broadcasting data. So basically, one example is like broadcasting TV data. So data that is coming normally over a TV signal, that data, that same information could be sent over the mobile network. So basically, you will be able to receive like multimedia or receive like broadcast data using using the mobile network and then with your mobile device. So in that sense, we can reuse the infrastructure and then deliver also this multimedia data. And this can be done based on regions, or then it can be done based on schedule, based on different time of the day. Then we can distribute this data from the different applications. Also for emergency. So for example, if you need to broadcast a emergency message to a large amount of devices, then you can send that over this network. And I think that's the last thing I wanted to share. I mean, there's also information about authentication, but that's more related to security, which I will skip. Okay. Thank you.
Welcome to the lecture on 5G physical layer. My name is Antti Toskala, coming from Nokia Standards and Technology Unit based here in Espoo, Finland. And I will be taking you through this 5G physical layer, what it is all about, and what is also a little bit coming in the future as the next development steps. So first of all, here is this structure of today's lecture. We'll be going through different areas of the physical layer, starting from the key technology components, compare a bit what's the difference between 3G and 4G, and then go through these different elements, waveforms, frame structures, channel coding, and so forth. Finalizing with this small talk about what is the current availability in terms of devices, what do they support and what do they don't. And on the picture on the right hand side is then the reference material, so commercial part of the presentation, so the book written by not only myself but many Nokia colleagues, as well as colleagues from some other companies like MediaTek, Skyworks, NTT Docomo, that bring the expertise of 5G together. If you look the 5G radio technology, so what was new compared to the previous generations? So first of all, we had to deal with elements like new spectrum, meaning that we were addressing higher frequency band than previous generations. On one hand, we were also from the day one putting a lot of emphasis on dealing with the beamforming, which of course when you go to higher frequencies, antennas get smaller, then doing this kind of antenna arrays gets more realistic from size and cost point of view. So then the beamforming was now really taking into account from the day one of the radio interface design. Then this slicing flexibility, meaning is that even though we defined this kind of radio with a massive data rate and capacity capabilities, we also took into account that first of all, not every device may not be in the future needing these several gigabits of data rates. We also need to be able to be flexible, to configure the system in different ways, including to operate in a situation that you don't have that much traffic, that you want to save energy, to be energy efficient, to take these current climate challenges into account. Further, we are now really dealing with the multi-connectivity, meaning that with 5G we enable that we are connected together with the 4G LTE connection as well as 5G connection. This kind of dual connectivity we have practiced in the standards in the earlier generations, but now it's a real first time that it's really taken into use and is the baseline feature of all the devices you may already have in your pocket. If we now look what is then difference to this 3G, 4G from the radio technology point of view. We can see elements like take the waveform. 3G of course was totally different based on code division multiple access CDMA. Now with 4G we already took the OFF-DMA into use and we continue that with 5G, but we of course add a lot of more flexibility, as you later see, in terms of parameterization, where you can apply it low band, mid band, very high frequency band as well. Uplink waveform is another element, CDMA in 3G, single carrier FDMA in the 4G side, and now we have also OFF-DMA, orthogonal frequency division multiple access, together with the single carrier FDMA operation in uplink available. These technologies being suited for a little bit different needs. One suited for cell edge operation when you're power limited, other one suited for multi-stream uplink transmission when you have more link budget available. Channel coding was something that between 3G and 4G we only applied basically copy and paste, nothing major changes. But But now with the 5G, with the increase of data rates, challenges with the power consumption in the handset as well, we had to take something more efficient. So we took the LDPC, low density parity check codes into use. Technology known from, be that from these space missions, be that from Wi-Fi, but we did improve it, make it more flexible, more advanced compared to these previous generations of low density parity check coding. Beamforming, 3G did not really consider that in reality, 4G only partly, but now we have full support starting from the initial access as we discuss shortly. And from the spectrum point of view, previous generations were typically limited to 3G up to this 2 gigahertz range. 4G went up to this 6 gigahertz if we take the unlicensed into account. But now with the 5G, in the first phase we have done the support around the 50 gigahertz range, now working even higher, and will soon enable up to 71 gigahertz. So clearly a larger range of spectrum could be utilized. And that naturally is linked to this bandwidth we have up to 200 or even 400 megahertz bandwidths in the millimeter wave supported by the devices. And so additionally, we enable more energy efficient network operations, so really green networks. We are lower latency, faster decoding, shorter TTIs, transmission time intervals, as we see shortly. And many solutions that we developed in LTE standards did not necessarily implement, but now they are really rolled in the field in practice with 5G. So let's have a look in some of those interesting ones in more details. For spectrum point of view, indeed, even if I say now that we are up to 50 gigahertz, 71 gigahertz short, of course in the first phase you need to build coverage, and that's why the low frequency bands come to the play. We have those frequency bands like 3.5 gigahertz, as discussed shortly, is really the major band, also here in Finland and in Europe in general, but also being rolled out in US and Asia quite widely. And then this high frequency band then offer future capacity expansion. So if you take the 3.5 gigahertz band range as an example first, so there typically an operator has around 100 megahertz bandwidth. And that's something what all these first phase devices support. Every 5G device in the market today, if they support this 3.5 gigahertz frequency range, they support 100 megahertz bandwidth, which is clearly 5 times more than the basic LTE bandwidth. And that of course has a clear direct linkage to this data rates you are supporting. There are of course several existing LTE bands that have been specified as 5G bands. So over the years we will see refarming when operators will move more and more of their spectrum assets to be operated using 5G technology. This millimeter wave bands 28 gigahertz range, in Europe you talk more maybe 26 gigahertz range, was not used earlier by the mobile communications, and now it's been rolled out, but still slowly. It's mainly in US. In Europe you don't see much of that, if any. Like if you go and buy the latest iPhone in Europe, the versions don't support the millimeter wave. If you buy a version in US, they do. So that's also a clear indication that in the other markets those millimeter waves will come still later. So to be able to deal with this different sets of frequency band, you need a lot of flexibility in the system. And to enable that, we defined many different subcarrier spacings and are defining even more in the standards for later releases. And that was that For the low frequency bands, using the same as LTE, 15 kHz works well. But then you have, if you want to support larger bandwidths, then the amount of subcarriers you would need would tend to be quite large. And from the fundamentals of OFDMA technology, having very large FFT sizes would not be ideal. So when you go to this 100 MHz bandwidth range, you want to use larger subcarrier spacing so that you don't need such a huge number of those subcarriers. Same time with OFDMA, when we increase the subcarrier spacing, our simple duration in time gets clearly shorter. So that means that we go down in latency as well, meaning that how long does it take to transmit, for example, the typical 14 symbols. With the 15 kHz subcarrier spacing, it takes 1 millisecond. When we go to 30 kHz subcarrier spacing, it takes only half a millisecond. And if we go all the way to this 120 kHz subcarrier spacing, which is intended to the millimeter wave frequencies, it takes only 1/8 of a millisecond to transmit. That, together with faster processing times, is a key for enabling this kind of shorter round trip times in 5G compared to the previous generations. Then when we go to this millimeter wave, indeed, another issue comes that this phase noise becomes an issue, so that your frequency estimation is not necessarily so accurate anymore with the higher frequencies. That's why also the subcarrier spacing needs to be higher, so you are able to cooperate, deal with that, and you don't get too much interference between the subcarriers. That would be the case that if you try to operate 15 kHz subcarrier spacing on this 26 GHz frequency, for example. So then let's look the waveforms next as a next item. So in release 16, indeed, we have the OFDMA in both directions. In uplink, we have the single carrier option for the cell edge cases if we are limited with the power operation. The motivation for OFDMA, both in uplink and downlink, was to be able to have a similar solution dealing with the interference handling. Think about side-link communication. Side-link communication is the communication between the handsets. And OFDMA then allows this kind of efficient multiplexing of different services in the frequency domain, which is then needed as part of the 5G operations. Release 17 is addressing even further higher subcarrier spacing values, as we are addressing especially the 60 to 71 GHz frequency bands. That is mostly going to be unlicensed use, but in some regions also licensed operation on that band. But that clearly building for the future, something that could expect to appear in the market maybe end of 23, early 2024 timeframe. And currently the discussion in 3GPP is that we don't likely go above 71 GHz, as there are not new frequency bands now identified available for the 5G there, but some studies may be started to look for new waveforms. OFDMA with the very high frequencies is not necessarily going to be so attractive, so it's maybe more towards this kind of single carrier waveform type of considerations for very high frequencies when you go towards the above 100 GHz and beyond. So now if you look at the frame structure of 5G, compared what is the difference to LTE. First of all, similar to LTE, we support both FDD and TDD, frequency division duplex and time division duplex operations. Recall, with FDD you had to separate part of the spectrum for uplink, separate for downlink, but with TDD we were sharing them in time domain. Now with this reference signal structure, with LTE, the reference signals are, so to say, all over the place when you look the slide. That is to allow this kind of good interpolation to create this channel estimate both in frequency and time domain. This is nice, but it has one major drawback, is that you need to receive the whole frame before you are able to create your channel estimation. And that's only when you can start decoding your data. And that costs you in time. You introduce delay. With 5G, the idea is that you have first your control signaling, then you have your reference data that allows you to build a channel estimate, and then you are able to do the data decoding straight from the beginning, which means that ideally you are done with your decoding almost when your data stops coming. This has some drawbacks naturally for an environment where you move a lot, so that then the channel is changing too much, and in those cases we do need to add additional reference signals to the end. And that's why later when I show something processing times, you see two values as this extra demodulation reference signal. If that is in use, then of course device to need to capture that one before you can do the real full channel estimate and start decoding your data. Channel coding was perhaps the most controversial element of first 5G design choices we had to do in 3GPP. One thing was that also engineers dealing with this had been used with turbo coding since early days of 3G, and that had been specified in 1999. And now we were dealing with this, we had adopted the same solution basically for LTE as well, and now was kind of a big decision to change the situation and take something else into use when everybody had been used to that turbo coding is what we are using. The problem with turbo coding was the fact that devices with very high data rates would become really too hot in practice. And I don't mean the hot in design, but from the temperature point of view. So we had to really have a cooler devices so that the channel coding solution could not use so much energy, because that was the problem with turbo codes going up in the data rates. More and more energy is consumed in decoding the data. That's why we were evaluating these different alternatives, and we had also some other choices like polar coding into consideration. Was fairly new, but it did not offer anything, any real improvements over low density parity check codes, which were clearly superior in their energy efficiency and provided really good area efficiency as well, that your chip surface area is not too massive to make the decoder. So then low density parity check codes were chosen as the channel coding solution with 5G. For the layer 1 control signaling, we do some other solutions, sometimes repetition, sometimes Riedmüller, or sometimes this polar coding. But for real device performance, of course, it's the actual channel coding that makes a difference. Low latency comes from multiple elements. One thing indeed is what I have described, that you are really able to send data quickly, so that it doesn't take too long for data to travel over the radio interface. But other element is that once the device receives the data, how long you need to process that before you can pass it on towards the upper layers and eventually for the application you are using. And now, with the solution described earlier, the decoding can be now clearly faster, like you can see in the picture, in this easy case in the sense that you have FDD, meaning uplink is all the time available. Already during the next transmission time interval, you get the feedback for the uplink whether your data was received correctly or not. And if it was received correctly, then of course device can push it on towards the next layers in the protocol stack. If you compare with LTE, LTE was only done with the decoding some same time as with 5G we would already have a retransmission available. So that shows a clear difference between LTE and 5G in this latency performance, in the speed of decoding, as well as how fast you get the stuff over the air interface. Besides this 14 symbol, we have also other means to make it even faster. So we have this concept called mini slot, which means that you don't have to allocate full 14 symbols. You can allocate 7, 4 or 2 symbols, those called mini slot. And that again cuts time from the operations and can make the latency even smaller. Where would you need such a extreme latency? It doesn't matter if you're watching Netflix, but for this kind of applications in the industrial environment, for example, controlling the robots, machinery, this ultra reliable low latency communication, that is the field where it really makes a difference. Is the air interface delay? Are you dealing with 5 milliseconds, 10 milliseconds, maybe 15 milliseconds that we get typical when we test LTE as of today? But now we can go to this kind of 1 millisecond level or even smaller than that for best cases. There are more future-oriented structures in the specifications. One may, if you read the specifications or the book, you know these concepts like self-contained subframe, where also the uplink feedback would be encapsulated, already provided during the same frame where the downlink data came. Those are of course more for the future looking, not supported in the devices as of today in the marketplace, but may come to the play in the future as also processing technology gets all the time faster and faster. So now if we move a bit for the next section of the story, meaning the beamforming. So what have we done in 5G differently to earlier generations? So first, as I mentioned, when the higher frequency we go, already 3.5 gigahertz, the antennas get smaller, you can afford to include more antennas in the devices. And not to mention the millimeter waves, then the antennas are really small, and you can expect the devices have even the multiple set of antennas in them. Beamforming allows to boost the capacity. As you can imagine, that instead of having just one sector covering, for example, this building from the outside base station, you can have inside the sector different beams that have some isolation among themselves and really focus the transmission for that particular user or group of users needing data at given time. And that is the way like dividing this basically, like if you think about sector, something similar in that similarity. If you would think the idea that we go from 3 sector cell to 6 sector cells, we are splitting this kind of smaller pieces, the resources in space and frequency domain. Also with the beamforming, then when instead of not sending for the same sector or full sector, meaning indeed we focus the energy, we send the same amount of energy but focus in a narrower direction, not over 120 degrees but maybe 10, 20 degrees if you think about this 360 site, and that allows of course us have a better link budget and compensate a loss that we get with the higher frequencies. As you recall, the higher frequency band, the higher is the attenuation you get for your link budget. To deal with this beamforming operation, we typically apply this kind of hybrid beamforming, especially with the high frequency bands. So that means that the base station can only transmit at one direction at a time. So one beam can be active at a time. And that means that we need this kind of special measures also to be able to figure out which beam is the best one for a different particle device. And that's what we have, this what we call the beam sweeping, which means that we are transmitting one beam direction at a time, and device will measure, is it beam 0, is it beam 4, is it beam 5, what is the beam that I receive the best, simply meaning what is the strongest for me, and give that feedback for the network, and network then can use that beam for the device in the next transmissions. And that allows that we have this kind of continuous tracking when devices move around in the area that is served by multiple beams. Devices themselves can have directivity as well in the millimeter wave, but that's more detailed discussion on that one. On this kind of MIMO technology, multiple input, multiple output, we have a lot of different alternatives. If going into the deep details, it would be maybe a lecture of its own on the MIMO, but we can operate. This operation is often based on this CSI ARAS, so channel state information reference signals that the devices measure and give feedback for the network so that the network can configure the best possible beamforming transmission. We can have one of those, or we can have multiple those, depending what kind of beamforming array we have available in the base station side. And then the device measures, is told what is in use, measures all of those, and then provides feedback, suggestions that, okay, what kind of transmission would be good for me in a given point in time. For TDD bands, other element to use is this channel reciprocity, which means that because now we are using the same spectrum and same piece of spectrum for both terminal transmission and reception, which means that the signal then typically propagates, of course, roughly the same route for both for transmission and reception when we are talking about same part of the spectrum. And that's why there the possibilities is also used things like sounding reference signals. Device can also send this kind of known data for the network, and the network can measure that, and based on that figure out what kind of beamforming to use to reach such particle device. Sounding reference signals, that's what they are used for. When you go to this millimeter waves, again we have a lot of different implementation choices. One may do this kind of single panel array that is basically able to, with this polarization, maybe able to deal with this transmit drivers to create two different MIMO streams, but only one device at a time. We can do this kind of multi-panel array situation that can serve maybe one device with basically multiple beams or more MIMO streams, but typically the devices don't do many MIMO streams on the millimeter wave because it's not so beneficial. But more advantage solution is actually then when you have multiple panels to use it as a multi-user MIMO, that you try to seek this kind of devices like pairs or more than one device, that maybe they are a little bit in the other end of the area you are serving, and simultaneously you send one beam towards the other device, other beam towards the other device, and serve them simultaneously, and that way increase the sector peak throughput, but not of course the individual device peak throughput, but you are able to serve more devices in a given point in time. And then for that one you have indeed the same solutions. You can have this channel state information, you can use the sounding reference signals, but typically the higher frequencies you go, then more beams you can enable, also from the implementation point of view as well as from the standards point of view. The low frequency bands typically support only 4 or 8 beams to be used, while higher frequency bands can go up to 64 beams or even higher in the practical implementations, as well as from the specification support. For the layer 1 channel structures, basically we have this set of channels in use. We have uplink shared channel, we have downlink shared channel, terms known from the LT side as well. Physical broadcast channel is to send the necessary broadcast information. There's a downlink control channel, physical downlink control channel, PDCCH. Same way uplink direction, we have physical uplink control channel, PUCCH, and then the PRADS, random access channel for contacting the network in the first place before you have a connection up and running. And then we have physical signals, many of them known from the LT side. Some of them are new, like these phase tracking reference signals needed for the millimeter wave operation. Otherwise pretty familiar from the earlier technology. Reference signals for channel estimation, or channel state information reference signals for measuring the channel and providing feedback for the network. And then this PSS and SSS are the primary and secondary synchronization signals. Those are the ones you use to find the cells in the first place. For the synchronization and broadcast operation, we have this thing called SS block, and that is the one that the devices will seek first. So this is used to identify devices to identify what is the cell. So they find that from these primary and secondary synchronization signals. They get these things called physical cell ID, identify the cell, and then this broadcast channel gives the necessary parameters to access the network. And for example, where do I find the random access channel and other network parameters. And this sync block is indeed, when we have this earlier, what I showed, the beam sweep, is the sync block. This is what we send periodically to each of the beams. This is what the devices measure. Based on this one, what they find the network in the first place. For downlink channels, physical downlink control channel, PDCCH, this is in the first part of the frame in downlink direction. So first comes control information, then comes the reference data, and then comes the actual PDCSH symbol, so physical downlink shared channel. And we have a different formats for physical downlink shared channel, simply to use basically as a link adaptation. If we have device next door to the base station, we don't need a lot of channel coding because we have a very strong signal in that case. On the other hand, if a device at the cell edge, then we want to protect the signaling well because and use a lot of redundancy for the channel coding. As like every system, if you lose the control signaling, that tells you what you are supposed to receive in the first place, then of course it doesn't matter how well we send the data itself because the device will not know it's coming. So that tells indeed whether there's data coming for a particle device and where in the, for example, 100 MHz carrier this data is located. Physical downlink shared channel then comes after. Now I also have shown here the example of this demodulation reference signals that come after the control channel, and then rest of the symbols is used for this PDSCH unless we would have this additional demodulation reference signal in place. We have 4 different modulation size, so we have the QPSK 16COM, 64COM, and 256COM. And now in release 17 we are adding for downlink also this 1024COM modulation, mainly beneficial for this kind of fixed wireless type of access operation when you have a really good signal conditions. specific thing shown here in blue color. You see this continuous line. So that is this phase tracking reference signals that would be in place to allow the device to deal with this phase noise, to have this kind of known signal there in the millimeter wave operations. Clearly, on this kind of slower frequency bands, smaller than 6, or maybe based on the release 16, I could say below 7 gigahertz, you don't need this naturally, as you don't have such a problem with the phase noise. On the uplink direction, we have this uplink PUSCH, physical uplink shared channel. So first of all, the uplink transmissions, with the exception of the control channel, but for data, is always based that we get the permission from the base station when we can transmit in time domain and where in frequency domain. This allocation could be something that could be like repetitive allocation sometimes, but quite often it's dynamic to really not book the resources just in case, and that comes on the downlink control channel as well. And then in uplink direction we can have also the single carrier transmission besides the off DMA in place. On the modulation sides, it's the same set of modulations, but for this low peak to average ratio case, when you are at the cell edge, we also have this pi over 2p PSK in place. And then the device will then send this UE specific demodulation reference signal so that the base station, on the other hand, can decode the data. Physical uplink control channel is something that carries uplink control information. If you are sending uplink data, then of course you multiplex this together with the uplink data transmission, but you need to be also able to send uplink control information when you don't have uplink allocation. So then you can of course send only control information, where the key message is that things like, okay, my previous packet failed or did not fail, and or other way around that now I have data in my buffer, so to have this kind of request to get resources allocated. Further in uplink channels, so we have this PRACH, physical random access channel, and here the beamforming comes to the play. So now that beamforming is there from the day one, so that means that devices need to figure out not only from the broadcast channel that what is the resource to use for the random access, but also the devices do need to measure what is the best beam I should use. So now actually I need to select such a random access resource that is occurring in the beam that I measure that is best for me. And all this kind of that kind of information you get from the broadcast channel transmission. That what are the resources, and then I figure out, for example, in here that if this beam number 5 is the best for me, then I select such a random access resource that I know that when I send it, the base station is listening the beam direction number 5, because otherwise, of course, my random access resource will be wasted. But all that, when it has been taken into account from the day one, allows then to fully benefit from the beamforming, including when I'm accessing the network. It allows me, the network, to then direct the beam to the direction that I am, and then I get this maximum link budget also from a random access operation. Because otherwise, if the random access would be then this omnidirectional channel, but then otherwise I would be using beamforming, and then it could be a situation that the data connection could be maintained, but I don't reach the network because my beamforming doesn't support random access operation. But that's why it was important that beamforming was there from the day one, part of the design, as these kind of things are often difficult, if not even impossible, to add afterwards for the system. So now here also you have the term beam association visible, which means basically that in downlink, if I receive the beam number 5 being the best, then indeed in uplink I should understand that that this is what I use in the random access. And then ideally also when you think about the millimeter wave, if there's some directivity in the handset, it should understand that if the particle direction where my best beam is coming, if I have any directivity, I should also direct my transmission to the same direction and not somewhere totally different. So that's the meaning of the beam association in that sense. So what are then the first phase devices all about? So basically the first phase devices that came to the market 2019, they were supporting already, which was the first mode of 5G operation, this kind of dual connectivity. That was referred like non-standalone 5G, that you first had to access LTE, and then when there's enough stuff to transmit, then the 5G was activated on the side. The current set of devices, including the example devices on the slide and what I'm having here, this is like a Nokia 8.3 5G. So they do support the standalone 5G operation, which means that networks that are now moving to this, that you can directly access 5G. You don't have to first go via LTE, or you don't need to have LTE on the connection active. That will allow also smaller latencies. You get all the 5G benefits, faster connection setup when you don't have to go through LTE. And then when you do a test, you don't get only higher data rates, but indeed the part of the package then does not go through via LTE channels. Then that allows that the latency overall is smaller. And we can get already in the market pretty high data rates. So this example number taken back home in my place outside, of course, then I get this nearly 900 megabits, but still also inside I get, depending which room, 600 to 700 megabits data rates, which is quite impressive. But I happen to live relatively close to one of the base stations by one of the operators. And the devices, indeed, they all support this in the European market. They typically indeed don't use the millimeter wave, but they support this 3.5 gigahertz band, often referred as a C-band, that supports 100 megahertz carrier. It's a mandatory for device to support this 100 megahertz. It's mandatory for device to have 4 receiver antennas. So that gives this kind of device capability in the order of 2 gigabits as a peak data rate. That could be achievable basically that if I was the only user for that base station and very close to the base station, I cannot get that kind of data rates myself for a given reason that of course my subscription has some limits that will not give me 2 gigabits. So then there's no point for me going even closer to the base station as then my subscription will start limiting this. But at least in my case, I can see that I'll get quite impressive speeds, and I'm going to ditch my ADSL connection that gives me 10 times less in very near term in the future, as soon as I get rid of my existing DSL contract. And in the US market, indeed, the devices support this millimeter wave operation with 2 receiver antennas. You don't get, even the antennas are very small, you don't get that much diversity in the channel you get with this 28 gigahertz, because propagation is such that if the signal reflects somewhere far, it gets already then so much attenuation. So that's why it's a 2-stream MIMO only for the millimeter waves. But but of course the bandwidths are larger. Devices support 400 or up to 800 megahertz of bandwidth, and there you can get this kind of in the order of 4 to 5 gigabits data rates possible with that kind of deployments. But in most markets, the millimeter wave is still coming, and also on the standard side, we are still doing a lot of improvements to make the millimeter wave operation even more efficient and more reliable. But with the millimeter wave, of course, it will be more for the hotspot, more local, as the coverage on the millimeter wave is going to be limited. And like in this kind of campus, you would really need indoor base stations from the outside. It doesn't really come through the walls in practice well. And so this is then still basically the summary, what I have described. So we have a high performance radio in place, also supporting the millimeter wave, but those come later, especially the European market. And all devices support the dual connectivity, now later the standalone 5G operation, and we enable really high data rates, low latency with this, and we expect many different uses in the industrial case in the future. Then final remark is that if you think 5G is your thing, you are eager to learn, not only here in Aalto University, but in the future a part of your career. Also from our side, we are continuously hiring people for Nokia, getting new talents to work on this exciting developing of 5G. So please follow our offering. Here are a couple of examples available as of today. Thank you very much.
Okay, good afternoon, everyone. Really great to see you here. We are now about to start. My name is Sasu Tarkoma, Professor of Computer Science at the University of Helsinki, and also the head of the Computer Science Department. And today I will cover AI and 5G, especially focusing on deployment aspects. So that's the topic for today. And as we know, AI is now a very hot topic, and we have more and more applications running over 4G and 5G networks, having AI elements. So it makes sense to study what 5G can do for AI, but also we need to study that what AI can do for the network itself. So these are the interesting directions here, and I will explore these in my lecture. So now to get going, so today I will give you a brief introduction to the 5G architecture, and I will focus on edge computing and then how AI relates to edge computing and the paradigm we call edge intelligence, which is really in a way the combination of edge computing and AI methods for supporting the network and for supporting the applications. And then I will briefly discuss recent work in the 6G area. So of course we have now 5G, but then after 5G there will be 6G, and we are already now looking at what things will be important in 6G. So I will talk a bit about the 6G white paper on edge intelligence and how some of these components, some of these notions might then be part of the forthcoming 6G architecture. And then I will focus more on the examples related to deployment of AI and of sensing through 5G and beyond systems. And I have a number of cases that I will cover. And these cases are motivated by our current research in this area. So I will focus on how AI can help us engineer and deploy better networks. So we call this network and slice generation. I will talk about network security, so how we can deploy AI into the network that would then make the network safer, would protect us from different attacks. And then I will also focus on AI for sensing, for environmental sensing, and also for sensing in industrial settings as well. And then we have a brief conclusion for the topic. So these are the topics for today. And now to start with 5G architecture. So of course, 5G is part of the continuum, so that we have 4G and 4G having very good properties for mobile broadband, but then for some other cases, verticals like massive machine type communications for IoT and for ultra reliable communications, 4G is very limited. So we have certain requirements that our applications today have that are not met by 4G, and 5G was intended to address many of these emerging requirements. And the three key areas are now presented by this diagram. So we have enhanced mobile broadband, we have the machine-machine type communications, and then we have ultra-reliable and low-latency communications. And these address a bit differing concerns. And the takeaway is that we have different applications having different requirements, and the network should accommodate these requirements. So we should have flexibility in the network programmability that would then enable us to accommodate these different requirements. And for 5G, we have these three key domains, and these also correspond to three network slices. So network configurations, then having good support for the use case. And now looking beyond, so of course we have also combinations of requirements across these three areas and so on. So the world is not done yet. So we believe that in 6G we will have even better possibilities of taking application requirements into account when we tune the network for the applications. So that's the direction we are heading at the moment. And we know, of course, that the application requirements are very heterogeneous. Here you see a diagram illustrating the delay and the throughput requirements, expectations of well-known application areas. And you can see that we have really, a lot of different requirements by the applications. So there is no one size fits all for the applications. And we have some of these more straightforward applications like monitoring networks, sensor networks, in which we have a very kind of good tolerance for delay, and we do not require a high throughput. And then we have applications like tactile internet, where we have really high demand, so very low latency and high throughput is required. And now our network should be able to accommodate these different cases. And thus we kind of can approach this from the challenges point of view. So looking at the different use cases, applications, so what are really the problem points, what are challenges there? And in many application areas, so we do have the requirement for local computing power, that we do something that's very intensive, and we need to do most of the computing locally or within the region to keep the low latency requirement. So that's one observation that we can make, and certainly low latency is something that is needed for many use cases. And of course, for some current and many emerging applications, so we have also increasing bandwidth requirements as well, like for example, AR and VR applications and so on. Of course, we have 8K videos and such for the mobile broadband side as well. So we see these as crucial challenges. And then we have privacy aspect as well, that we do data gathering, and we need to, of course, ensure data ownership. We need to ensure data privacy. And we can ask that what can the network do here for the applications? And for many of these, we see that we can support the applications by having computing near the devices, near the handsets, near the sensors. And this is edge computing. We bring in computing capabilities, these other resources at the edge of the network, and open up those resources for the applications so that we can do distributed computing that can take locality into account. That's really the essence of edge computing. And we see this as a kind of interesting element that is now being deployed over 5G and is part of 5G, and will, I believe, certainly be part of 6G as well. So edge computing has a role to play here, and how to support applications, and also how to support the network as well. So now just summarizing some key aspects of 5G, that what is happening with 5G and the different kind of iterations of 5G. So of course we have the radio access network part, and there we have better radios, we have new spectrum for 5G, and many innovations that help to improve the data communications. And we have also cloud, so virtualization is having an effect here, that we can do baseband processing in the cloud, and also at the edge of the network, and that's in a way paradigm shift for many things, that to have the cloud support our activities and support the base stations. And then for the core network, so for the more fixed network part and the cloud part, so we have a service-based architecture, and we have the network slices. So better support for programming the underlying network and its capabilities to meet the requirements of the applications. And we have 3 slices and of course going beyond 3 slices as well. And then we have this edge computing capability for supporting the applications with this nearby computing, the capabilities that what we have through the network. So this is what we are now having in 5G. And of course, there are still many iterations to be done in 5G to get most from these developments. And then we have the 6G coming up to kind of continue this evolution of the cellular architecture. And now to provide some details on this network slicing. So of course you may have heard about this already. So and I already gave a very short definition of the network slice. So so it's really about this programmability of the network, being able to have the network slice that consists of the RAN part and then the core network part, having these network functions placed over the slice. And the network functions, they relate to the network itself, and then also to added functionality that the network is able to offer. And this needs to be provisioned and managed, and through this we get better utilization of the hardware resources, and that can also better then accommodate the application requirements. And the network slices are now being piloted in a way. So we have 3 slices, and my expectation is that in the future we would have more than three slices, but this is part of the evolution of the network. And then we have something like this, that we have the slices, we have the different network and also application capabilities then distributed over the slices and then over the edge servers. And what is really interesting here is that how we then deploy sensing and AI capabilities. So application-specific sensing and AI capabilities over the network slices. And this is something that we have been investigating quite a lot in recent years, that how to do this for different use cases, and how to generate these slices, how to generate the configurations, and then place these functionalities over the network. And this is, of course, something that is forward-looking, but already in today's networks, we have some of these characteristics in place. There is a lot of optimization being done in how the network slices are kind of maintained. But from the research point of view, this especially the sensing and AI capabilities, so that's still an emerging direction, and there are many interesting questions still that need to be addressed. And as a kind of key takeaway, so programmability is now the key here, that we're able to program the network slices, we're able to program the deployment of the sensing and AI capabilities, do the optimization of this, do it offline, do it online, and this then would ensure that we are able to kind of optimize resource utilization and then meet the requirements of the applications. And what is very interesting here is ORAN, which is a set of open specifications for opening the radio access network. So ORAN is really aiming to open the RAN and have cloud native interfaces for then connecting these RAN related components and enable to program these. And this is very interesting because this enables component reuse, it enables flexibility in RAN design. It also supports innovation. And especially from the academic point of view, so it's very kind of difficult sometimes to do very hardware-oriented RAN access network research. So ORAN would help there as well in terms of supporting researchers, and would help also pave way from the lab work to an actual product as well, to speed up the innovation cycle. So ORAN is very interesting, and what is also interesting here is the radio intelligent controller that's specified by the ORAN activity. And this radio controller would then help us to configure AI tasks and activities for the RAN domain. So of course we have controllers now for the core network side, but it's been an open issue that how to do this this in a way standard-based and interoperable RAN control, and the RIC controller here is a step towards that direction. And this is an evolving set of specifications, an evolving initiative, and of course we stay tuned for updates here. But it's very interesting from this kind of innovation point of view, and would help in exploring new designs for how to have AI in the radio access network. And now we go forward to edge intelligence, and we see that we now have the slices, we have the edge computing, we have the radio access network and the RIC controller. So edge intelligence now kind of comes into the picture and helps us to kind of coordinate these to then get to this more optimal situation for the application, and take these different concerns we have been now looking at, like latency and processing power and privacy and so on into account. So edge intelligence really, it's about being able to offer these basic resource-related services like data collection, caching, data processing, data analysis in the local environment. So being close by to the devices which then produce and consume data and the results that we then produce. And of course, we gain the latency benefit and we gain the privacy benefit by doing this. And we have two directions here. So we have AI for edge, which is really about having AI help in doing radio management with the RIC, with the, for example, the cloud RAN, helping with network management, helping with network slicing, doing function placement, and so on, supporting also the applications. So, so AI has many things to give for the edge and for the network, but then we do have also the edge for AI view, in which edge servers, edge computing helps AI applications. And here we have the distributed and decentralized paradigm for applications, that how do we learn in a distributed environment and utilize edge servers for learning, for inference, and so on. And in recent years, we have had really many kind of foundational contributions in this area. For example, we have federated learning, we have transfer learning. So we have these building blocks that we can use to then create these distributed AI solutions. And edge, of course, it provides also the programmability point of view. So the applications can be then connected through the edge to the information we have about the network, about the user devices, about base stations. So we can do, for example, quality of experience monitoring and optimization through edge servers. So in a way, connecting the application view and concerns with the network view and the network concerns. So we can bridge these two worlds through edge computing. And then certainly we have the privacy and ethical data management as things we can then do at the edge of the network. So to kind of summarize the current direction, so we go from the left-hand side here, which is the centralized cloud-based AI that we frequently today employ, to the right-hand side, in which we have this distributed and decentralized AI being used, so that the AI, the model creations or learning, and also inference, they are highly distributed over the environment. So over the network elements, over different clouds, all the way to the end devices and sensors. And this is a very kind of interesting and highly likely future direction in which we are now progressing. And we are also having some of these foundational ingredients to build this infrastructure. For example, federated learning is one example here. Edge computing is, of course, a key ingredient, and so on. So we are now, in a way, realizing this distributed computing vision that I believe is not very new. So I believe we have had this vision for many, many years in computer science, for example. But now we are kind of progressing towards this vision, and 5G and then 6G are very important steps here in how to distribute this processing and make the network more efficient. So that's the trend that we have at the moment. And we have been now studying edge intelligence. It's many forms, many phases, through doing literature study, and of course by developing methods and studying the methods. And through the study we have now conducted, we have identified 4 key sub-areas in edge intelligence. So we have identified edge caching relating to data management. We have identified edge training, so building the models, learning. We have identified edge inference, so using the models, doing predictions with the models, and then edge offloading, which is about using the different resources we have in the environment to offload these different, for example, learning and inference processes, tasks over the environment in different, with different strategies. So 4 key sub-areas having certain more elementary building blocks and of course parameters and so on. And as a takeaway, so we can conclude that we have a fair amount of work done in this area. We have some good baseline solutions, but of course there is still quite some work to be done here in using what is already established, and then addressing also new concerns, new features that are needed. And this is, of course, something that the scientific community is very active on at the moment. So we have really high level of activity in the international communities working around edge intelligence. So just going through these different sub-areas. So the caching aspect, of course, is very important, that we want to ensure the reuse of data and ensure that data is available when needed. And these are, of course, the key things that where caching can help. And we can do the caching on multiple levels. So at the devices, we can do it at the base station, such at edge servers, in the telecom cloud, and of course in some more far away cloud systems as well. And especially interesting is the caching at the edge of the network and in the base stations. How to kind of support that. And for content, of course, caching is everyday activity. So we have established practices how to do caching for content, but for the AI kind of aspect, so there we still have work to do, how to cache the models and model updates and basically streamline the processes that how we operate with machine learning models in the distributed environment. So data management is still a partially unsolved challenge when it comes to distributed decentralized AI. So there's work to be done there. Then we have the model building, so the training part, which is really very interesting. It's of course very demanding. So building models is not easy and it takes a lot of resources. So optimization and use of accelerator components is really fundamental here. And this is where we see a lot of interest at the moment, that how do we create machine learning models in the decentralized distributed environment, in what use cases we actually need to do this, where we benefit from this, and how we use the available hardware resources in an optimal manner, for example, accelerators and such. And there I believe that there is much work still to be done here in terms of orchestrating the distributed decentralized learning processes over the environment. So orchestration is the term that is frequently used, how to kind of achieve this innovative deployment capability, that we are at runtime able to have these learning tasks, inference tasks distributed and configured over the environment for meeting the goals. And orchestration is a very exciting area at the moment. So we need orchestration for 5G, and certainly we will need new solutions for 6G as well. And optimization in its many forms is really fundamental here. As baseline solutions, I've already mentioned federated learning, and then we have transfer learning for then adapting the models to new use cases. And that's also a very interesting direction, that how can we really reuse the models that we then create, for example, in IoT and in the industrial setting and so on. And that's something that is now attracting a lot of interest in the research communities. So then we have inference, so using the models, making predictions. And in many ways, this is more straightforward than building the models. So in a typical case, it doesn't require that much hardware resourcing, but of course may require to some extent, so that we have the accelerators that we need to utilize, and also various compression techniques for managing with resource constraints. So we may have a very big model, so how do we work with the limited resources available at the edge of the network, for example, or on IoT devices. So I would mention also resource constrained operation as something that for which we have already solutions like compression solutions, but we still have many open questions in this area, that how can we do more from the theoretical point of view and also from the practical point of view as well. And then we have the offloading, so that we use the hardware resources. We are able to send the tasks to different hardware resources for completion. And this relates also to the orchestration I mentioned. And it's a central part of the system, of course, that how to do this. So now looking at the activity levels, given the published works in recent years. So we have been studying this, and the summary, so the takeaway from this analysis is that we have more and more interest in the edge intelligence area altogether. So you see that there is this linear growth in terms of the number of applications published in the area. And we have different subtopics here. So we have the caching, and for the caching, you can see that we have this downward trend So perhaps we can, as a takeaway, say that caching doesn't seem to be as trendy and as popular as some other topics within this framing of edge intelligence. So we have edge training, gaining some ground, then offloading, gaining as well, and then inference is really becoming more popular. So due to federated learning and other techniques as well. So you could say that this distributed decentralized learning is really booming at the moment. So there is really a very high level of interest to these topics. And now, so just to mention the 6G direction. So going forward in the presentation. So 6G really builds on what I've been now discussing so far in terms of edge intelligence. So we have the distributed and decentralized learning capability. We do inferences, and we do this over the cloud and the programmable network infrastructure. And we then, through the 6G activity, so we have the 6G flagship at Oulu. So through that activity, we set out to prepare a white paper on edge intelligence, so the 6G white paper. And you can find this online, and it provides views that how we go from 5G to 6G in this topical area, and identifies also key challenges that are still very much open challenges and would require further work for then getting those forward and then as possible solutions to 6G architecture and 6G systems. And we have two parts here. We have AI for edge and then AI on edge. So reflecting the two directions we have been discussing, and a number of then more specific challenges and points within these. And also overall, we see that there are different levels of distribution that we have here in edge intelligence. So we have the extremes. So at the top, we have the extreme that we have everything in the centralized cloud. And at the bottom, we have the other extreme, that everything is running on an IoT device or the other device. And then we have these more intermediate levels in which we have these different learning and inference tasks at the cloud or at the edge or at the device. So it makes sense to study these different combinations, how to do the distribution. And here one important consideration is that how much training we can do on the cloud and then on the edge. So that's a clearly a very kind of a big requirement if you want to do training, so model building at the edge and on the devices. So that will require quite a lot of computing resources. So we have to understand, of course, these aspects when we then develop the orchestration, when we develop the methods that how to really get to this more decentralized, distributed world. So the cloud white paper provides insights to these, and as a takeaway from this, so the key point is this having the different kind of levels, different layers of distribution affecting the learning and inference tasks, that how those are placed over the network. And it's really the orchestration that then manages this. So now going beyond the current discussion, so we go more for the concrete examples. So we will now look at the network and slice generation, and then the security, and then the sensing examples I mentioned already. So we will now go into these. And to start, so we have the network refactoring as a kind of method that we have been working on for many years to understand that how could we kind of repackage kind of refactor networks to accommodate application requirements. And of course, the vision here is that we would be able to take the specification that what the application requires, and then we would be able to reconfigure the network and generate the network that then meets these requirements and has the slice properties and the functions placed and the orchestration mechanism then supporting this activity. And we have been now working on a methodology to kind of try to achieve this. So we have certain steps here for the methodology. So we have first this modularization part, that we kind of take the current network architecture and we break it into parts. For example, here you see the LTE, so 4G architecture that has been modularized. And then we study the state variables and then study signals between different functions, different interfaces in this modularized architecture. And that way we can then start to do this refactoring. So we can then combine modules to meet the given goals. And here, for example, as our example, so we have the LTE, so 4G baseline architecture with certain signaling costs for these key network functions, features. We are then able to do this refactoring, and we are able to create, for example, a thin edge in which we have very simple base stations and most of the complexities in the network. And then we have intelligent edge in which we place most of the network functionality at the edge, so that the edge in a way is almost self-sustaining, highly resilient. And now looking at the signaling costs, so this intelligent edge actually now minimizes the signaling cost. So it has certain favorable properties, but the cost is that it has a lot of functionality now at the edge of the network. So this way we can study different kind of network designs, different ways of packaging network functionalities, and then be able to meet the application requirements in terms of resilience, signaling cost, latency, and so on. So it's a start here, and then we, of course, now would want to continue this line of research and apply this for 6G, for example. So that's one outlook that we have. So then now considering security, so we of course would want to detect any security threats in our networks as soon as possible. And in this collaborative research, so we studied this problem, and we set out to detect anomalous IoT devices by looking at the network traffic. So basically, we do a fingerprint of the first packets an IoT device sends, and then we do the security analysis based on these fingerprints and on the network utilization behavior of the device. And we, as background, we have data from these different IoT devices, what are their typical behaviors, and this then allows us to classify these devices into different levels of isolation, so that we can, for example, trust devices that follow the patterns that we expect, and then if we see that there are anomalies, so then we kind of start to do this isolation of the devices that we cannot really fully trust these devices. And we implemented this, and it's a step towards having this kind of AI system for securing our networks. And this can be also, we deployed this with Wi-Fi, but this can be deployed also with 4G, 5G, and these technologies. And especially here, the O-RAN I mentioned is an interesting direction, because it enables us to obtain information from the RAN, radio access network, so that we could do anomaly detection with even more data from the wireless domain. So that's very interesting direction for security research. But certainly security is a very important service that we can provide at the edge of the network. And AI has a very big role here for security services. Then, I would also now still want to mention two cases. So one is the industry case. And here you can see an overview of this, so that we have the central cloud, we have these deployments, and in this case we have studied the use of 6LoWPAN, so personal area network, to connect the different industry IoT devices, and then 5G for then connecting these 6LoWPAN deployments with the cloud. And we have different cases here. So one is that we first connect with the edge, and then the cloud, or directly connect with the cloud. And we have been studying the benefits of edge computing and looking also at the properties of 6LoWPAN for industry-oriented networks. And here, one takeaway is that the edge does have benefits, so that we gain latency by doing edge computing. So latency is really the key benefit, and as other takeaways, so we can conclude that 6LoWPAN works reasonably well for the industry cases, at least based on the empirical experiments we carried out. And we have been doing the experiments. So just highlighting one aspect of the experiment. So here on the right-hand side, top right-hand side, you see the latency of the sensors to the cloud and to the edge. And you see, of course, now a big gap here between the edge and cloud latency. So this is, in a way, the benefit of edge computing here. Enables us to really have a lower latency. And the application in this case has been anomaly detection with LSTMs for the industry data, especially power data and then HVAC related data. So then, so going beyond industry sensing, so we have also environmental sensing. That's really interesting as a scenario. And here we have studied the deployment of low-cost sensors and using AI to calibrate these sensors and process the data we get to produce pollution maps like this one. You can see here at the bottom right-hand side of the slide. And we have really some favorable results around the calibration aspect, so that we can really, by using ground truth data from higher quality sensors, we can then boost the capabilities of lower quality sensors and extend their accuracy and also capabilities. And just to show you that we created our own sensor device, so you can see it here. So this is a low cost, small form factor sensor device monitoring particulate matter, ozone, and some other properties. And we use edge-based AI to calibrate these and get to a reasonable level of accuracy for the air quality sensing. And we have been studying this as a kind of a long-term research activity. And now, so considering the 5G angle, so here we have two interesting considerations. So we have the low-cost sensors, and we are working on sensing as a slice, so that the network would accommodate high-density sensor deployments, and it's something that we can do with the machine-type communications support from 5G, and also mobile broadband can be used there as well. And then we are also studying hyperspectral cameras. So we extract air quality information from hyperspectral camera data, and there the images are very large. So there we have to have this mobile broadband support due to the bandwidth requirements. And we have been studying these. And as conclusion here for 5G, so we see that one size doesn't fit these different cases that we would want to have in environmental sensing. So we have very low data rates, but very high density of sensors. And then we have these really high data rates as well with the hyperspectral cameras. So it's a very kind of interesting scenario for 5G to then support because of these requirements. And we have been studying these. And now just to show you some results. So comparing 5G to 4G, so we observe in general this latency improvement that we didn't really observe so much throughput improvement when changing from 4G to 5G for the local sensors and for the cameras, but for latency we did see the significant improvement, 28% for the local sensors and then 17.6% for the cameras. And then we studied the use of edge computing and understanding the provisioning of edge computing for local sensors, air quality sensors, and then for the hyperspectral cameras. And here, of course, we know that edge matters. So as mentioned, so we get lower latency through edge computing, and then we also alleviate certain privacy challenges and data processing challenges as well by having a local processing of the data. But the provisioning then has many dimensions, and we observed in our experiments different trade-offs between CPU, GPU, RAM, and so on. So these are interesting takeaways when then considering a larger scale deployments of these systems. And this is something that we are now studying, that how to kind of support the scaling of these sensing deployments. And now the final point I want to mention about the deployments is the one we did with the network slice in collaboration with Aalto University. So we connected our local sensors to this slice, and then we experimented that how many VMs do we need to accommodate this growing number of sensors. So we did this kind of a scalability study. And we used a kind of baseline VM, so 4-core, 4 gigabytes VM, and then studied that what are the limits in terms of the number of sensors. And based on the experimental results, so we see this kind of a scalability limit between 10,000 and 20,000 sensors for this configuration. And then this has enabled us to study that now, what if we want to scale to, for example, Helsinki-wide sensing system, or take some other bigger city? So how many VMs do we need? And we have been now analyzing this. So let's say that we have two different configurations. So we have dense network with 400 sensors per square kilometer, and ultra-dense network with 10,000 sensors per square kilometer. So then for the dense network, we need 9 VMs for the Helsinki area, and for the ultra-dense network, we need 214 VMs. So we of course now see the cost of scaling here as well, and this is of course important that we understand also in a way the deployment characteristics of our systems, that how we use edge, how we use slices, and so on. To be able to provision the network and then ultimately generate the network that's optimal for this given deployment. And that's something that we see as our future direction. So now I'm ready to wrap up. Just to mention that we have the Edge AI Special Interest Group in Finland. So we have a community of researchers working on these topics. Connecting two flagships, so the Finnish Center for AI, so FCAI, and then the 6G flagship led by University of Oulu. And we organize webinars, we organize events. So if you're interested, please visit our website and join the community. So it's a very exciting area, and many things are now happening. But now, thank you, and I believe we have some time for discussion. Do we have any questions from the audience? So we have still some time. So if you have any questions, so please just ask. You can write to the chat.